a couple of weeks ago, there was an attack on a platform called bZx. And here's a headline from an article. So decentralized platform bZx sees an $8 million hack from one misplaced line of code. And yeah, I'll in this talk I'll try to explain how this could have been avoided if they just did a little bit of property-based testing. Yeah. So just as an outline, first I'll briefly describe the attack and where the bug was and how it could easily have been fixed. And then I'll have a short digression into property-based testing, what it is and how it works. And then, yeah, I'll talk about how this could have been discovered with a property-based testing framework that I've been working on. And then lastly, I'll mention some other vulnerabilities that I've discovered with this testing framework. So for context, bZx is a decentralized finance platform on Ethereum with lots of products built on top of it, like mostly wallets and lending capabilities. And so a key part of their platform or of the protocol is this iToken contract. So it's an ERC20 token. What this means isn't so important for now, but it's supposed to satisfy some specification about how these tokens should, well, what kind of operations it should support and how they should work. So these tokens represent assets of any kind on this platform. And so they have a value in some sense. They claim that the protocol has been audited, that the entire protocol has been audited by security firms PeckShield and Certicate. Supposedly 19 person weeks were spent in total for the audit, and they claim to have done extensive testing on top of it as well. But even so, the attack occurred, and initially they lost $8 million worth of funding, but yeah, luckily now it has been returned by the attacker, who was quickly identified. It's also worth noting that this bZx platform this is not the first time that they've been attacked. Back in April, I think, there was a previous attack called the Uniswap exploit, which also resulted in a loss of funding, which was then also returned by the attacker back then, but still the attack occurred. So this is not the first time. Yeah, let's just describe the attack. It's very simple. So the iToken contract, it has a transfer from function, which transfers from one account to another some number of tokens. And due to an implementation error, it turned out that when the sender and the receiver is the same, so you're transferring to yourself, well, you'd expect that your balance of tokens would be unchanged, but it turns out that due to an implementation error, you would gain the number of tokens that you transferred. And it's below is the code from the transfer function. And so it's quite simple. First, they store the balance of the sender and the receiver in two variables in line 1 and 2. And then in line 3, the new balance is calculated for the sender just by subtracting the number of tokens to be sent. And then in line 4, the balance of the sender is updated. Then in line 5, and this is where it goes wrong, so the new balance of the receiver is calculated by adding the number of tokens to be sent, but it uses the balance which was calculated in line 2. So it doesn't use the balance after subtracting the new balance of the sender. And in the case where the sender and the receiver is the same person, you would now magically have gained a number of tokens. So the fix is of course really simple. You just move line 2 in between line 4 and 5. So now it's fixed, and that was the bug. Done. We're done for today. No. Let's first talk a little bit about property-based testing, and then we'll return to how we could have discovered this bug. And some people also call it random property testing, but yeah, this is the term we use here. So on your left, you see an example of a property-based test where it's sort of just written as a pseudocode, so it's not some specific library or specific language. You state that for all x's and y's and so on, such that some precondition A holds on these variables, then it should be the case that P is true. And this intuitively, this should model the mathematical proposition that for all x's and y's, A implies B, A implies P. Yeah. So just as a brief historical remark, it was the technique was popularized back in, I believe, the 90s or early 2000s by with Haskell's quick check library, and there have been many ports of this library since then. Specifically to the cut proof assistant, it has a library called quick check, which is a direct port of quick check from Haskell, and that's the one I've used. So the property from before, we need this property to somehow be testable, and here I present how how we can interpret this property in a testable way. So the property starts by saying for all, and of course we can't test something for all values of something because that might take infinite time. So the interpretation is just that we run the test many times, like 10,000 times, and assert that there were no failed runs. Of course, like this is not a sound way of doing it, but that's never achievable with testing. And then we need some way of getting these variables x and y, or values. And the way we can do that is by assuming that we have some function which generates random values. So for example, if x and y are natural numbers, we assume that we have some function that generates random natural numbers. There's a lot more to be said about how to generate random values, but let's not get into that. Then the precondition A, so it's supposed to model the left-hand side of an implication. So in the case where A doesn't hold, that corresponds to the fact that the implication is trivially satisfied. So let's just go back here. The property on the right hand side, if A is false, then of course the implication holds. And in the testable sense, we just discard the test whenever A doesn't hold. In the case where A actually holds, then we just test that P should also hold. And if it doesn't, then it reports a counterexample, namely the x's and y's, which cause this property P to not hold. Of course, the properties A and P in this example, they must be executable in some sense. So for example, they could be Boolean predicates, but they don't need to. They just need to be executable in some sense. So let's look at a quick example. And this is this example is written with the quick check library from the cut proof assistant. So suppose we have some function remove, which is supposed to remove an element from a list. We can test it in the following way by stating a property that for all x's, which is a natural number, and for all lists L and L prime, if it's the case that x is in L and L prime is the result of removing x from L, then, well, then obviously X should not be an L prime. So this is not pseudocode. This is something directly written in COG, and we can actually run quick check on this property and test it by running, generating thousands of test cases and checking that that every one of them satisfies this property. So yeah, this is just to get some idea of how you actually work with these tests. One key point here is, of course, that the remove function here is defined on any lists, like list element type, but we had to specialize it to natural numbers, say, or it could have been booleans or strings. We have to test it on some specific type of lists, like natural numbers, lists of natural numbers. So yeah, just briefly want to just mention the pros and cons of property-based testing. So of course we have a high input scope coverage. This means because we run thousands of tests on random data essentially. And as you saw from the previous example, there's a high degree of automation. We just had to state the property and run it. Sometimes it's not that easy, but in best case scenario, that's the case. And we can express some really complex properties which are closely related to mathematical propositions. The one we saw from before with remove is, well, that's essentially a mathematical proposition, right? But sometimes we do require that the tests are executable. So not every mathematical proposition can, of course, be tested. But still, they closely represent mathematical propositions. Of course, a disadvantage of testing in general as an approach to having a high assurance of correctness is that, well, we can never show the absence of bugs, but that's more like a general disadvantage of testing, not just property-based testing. And furthermore, so in the case where the precondition did not hold, the test was discarded. And if the precondition is a very sparse condition, for example, let's say we test some properties on numbers, but as a precondition, we require that they are prime numbers with at least 10 digits. If we just generate and test this on arbitrary numbers, then the probability that they are prime numbers of at least 10 digits, well, that's an astronomical like chance that happens. So most cases would be discarded here. So that's of course a disadvantage, but it can be overcome by making custom input generators, but that may require some effort. Right. So now let's return to the question of how we can discover the bug. It was done. I did it in a framework called Concert. It's a formalization of blockchains and smart contract executions. It's formalized in COG, and it's also an executable formalization, so we can actually run the contracts. It's not just some abstract math. This was developed by Daniel, Jakob, and Bas, and a little bit me as well. Just as a remark, even though this is a formalization in a proof assistant, we can also extract to midline liquidity, and we're looking into also extracting to Rust. So this can actually be done in real programming languages. So now let's return to the key question of what is the property to test here. It's not necessarily immediately clear what we want to test, but at least it should be the case that we shouldn't rely on any knowledge of the attack. Because I'm doing this presentation now 2 weeks after the attack was disclosed, but ideally we would want to do it before the attack happens. We should not rely on any knowledge of the particular attack or of the vulnerability. Luckily, we don't need to get creative because there's it follows from the specification of the ERC20 token standard that any compliant contract must maintain a total supply of tokens somewhere in its state. And yeah, it's up to the contract whether this total supply is constant or dynamic. For example, the contract could supply mint and burn operations for creating and destroying tokens, or it could just be a constant amount. It doesn't matter. From this, we can state a safety property that that you see. Yeah, here it's I just stated I just defined it in COP, so please I hope the notation isn't too odd. But what the property says is that for any token state, if we calculate the sum of the balances, then it should always be equal to the total supply. So it's very simple property. Yeah. So of course, this property is not necessarily testable. There are some assumptions here. First of all, it was stated for an arbitrary token state. So somehow we must be able to generate token states. And of course, this token contract must be deployed somewhere on the blockchain that we're testing on. And furthermore, well, the endpoints of the token contract, for example, the transfer function, they must be called in some way, because otherwise we're not really testing anything, right? So I won't go into too much detail about how we can generate these token states and how we can make sure that the endpoints of the contract is called. It suffices to say for now that with this testing framework, this is possible. We can do it. We can generate token states, and we can test this property. And if we do that, the quick check tool will immediately report a counterexample. In this case, as you see, it says that it failed on transfer from, where the sender and the receiver is some address 10 in this case, and it sends 4 tokens. Then we could inspect the balance of this address and see that it has actually increased by 4, even though it should be constant. So yeah, we can test it, and with this tool, it actually discovers a counterexample. So let's take a step back and discuss a bit what did we actually test, and does it make sense? So I will make the claim that we didn't use any knowledge about the particular attack, or any knowledge about the fact that we knew that it was somewhere in the transfer function that that there was a bug. So, well, first of all, the property was just stated directly from the specification. So if they claim, bZx claim that this iToken contract is compliant with the specification, so it should satisfy this property. And the property didn't make any mention of the transfer function, and it didn't make any mention of the case where the sender and the receiver are the same. So we didn't really mention anything about the attack or the bug. But if you're not completely convinced, I actually tested this like half a year ago, like in March, I think, half a year before the attack occurred. But yeah, I tested on a bug-free variant, of course, because back then, well, I didn't know about the iToken contract or the fact that there was a bug. They didn't even know about the bug back then. But so I tested on a bug-free variant and didn't find any vulnerabilities. But then when Bas told me about this attack, I just inserted the bug into the already existing tests, and then there you go. We discovered the bug. So I think this attests to the fact that that even like we didn't rely on any knowledge of the attack because we did it half a year before it occurred. But yeah, so I guess the takeaway here is that property-based testing is quite powerful, because even for as complex of systems as blockchains, we can actually test these things. Um, and yeah, as we saw, the specifications are very similar to mathematical propositions, which as computer science, we computer scientists, we really like that. But yeah, it also means that we can combine testing and formal verification efforts. And that's kind of also what we've done in the Concert framework, or at least it's possible. Yeah, and an important remark is that although this testing framework is developed in COT, which is a proof assistant, we can it's the ideas and the techniques are easily portable to other languages like Rust or Liquidity. Yeah, and as we saw, we can actually discover real vulnerabilities. It's not just a theoretical application. It actually works. It's pretty cool to see. Yeah, so just for completeness sake, I thought I'd mention some other exploits. So this testing framework was something I developed as part of my master thesis in the previous semester, and there I did various case studies. For example, the Uniswap exploit that I mentioned earlier. We used the testing framework to rediscover this vulnerability or this exploit, and also the well-known DAO attack could also be discovered using testing. And there was another exploit of the transfer function for EIP20 tokens that we discovered. And I tested functional correctness of an FA2 token standard, and more recently also the escrow contract, which we also have implemented and formally verified in Concert. So yeah, it actually works in like real life scenarios. That's pretty cool to see, because it was just something I developed from my master thesis in the beginning, and now it's cool to see that it actually works. I guess that's the takeaway here. So yeah, are there any questions? I'm not sure how we organize this so everyone doesn't speak at the same time.
Yeah, I have a question. First of all, sorry.
Sorry, can you repeat? I'm not really hearing you quite well.
Okay. Well, first of all, congratulations on the 8 million. And then my question would be about property-based testing. So you said that you need your properties to be executable.
Yeah.
And I'm not sure why that would be, because so you're already, like you mentioned, the method is not complete, right? So you're not shooting for completeness. What's wrong with having properties that are not executable? You could still use proof search to try to prove them. I guess you might get some false positives if you can't satisfy a post condition. But I don't see the obstruction otherwise to use non-executable properties.
Right. Yeah. So yeah, it is. I guess it would be possible to also combine it with some proof search mechanisms. That's yeah, that would be possible. The reason why they should be executable is that well, you need to somehow. So let's go back a couple of slides. For example, so for example, in this case where we need to check that the precondition A holds, if it's not somehow executable, let's say, for example, it could be a Boolean, but if it's not executable, then we have no idea, we can't like compute and decide if it holds. We need to be able to decide it, because it should either report that the test was a failure or a success, or it should be able to discard it somehow. And if you can't do that, then how are you? You're not really gonna be able to come at like a, well, yeah. You need
if you can't satisfy the precondition, then in the worst case you're gonna discard a test.
Yeah, you can just discard the precondition, but then let's take the property P here in this case. Suppose that the precondition holds, then we need to decide if P holds. If you can't somehow decide that, then what are you going to use testing for? Yeah, it should be able to report a failure or success or something like that. Otherwise, you're like in an undecidable space that you, what are you going to do? You're just going to sit there and wait. But yeah, I guess the key point is that, so we want this to be effective in some way. For example, the test that I ran here and it reported a counterexample, I think it ran in like 1 second or something like that. And that's because the properties are some, it could be stated as a Boolean predicate. And that's something you can compute, and it's effective. And I guess that's a key usability point as well about it. Should be effective, should be fast.
But you're already firmly embracing incompleteness, so you might as well accept a few false positives, I guess. But yeah, so maybe something to consider.
As long as whenever it reports a counterexample, it should be the case that this is a counterexample. Yeah, we embrace the fact that there may be a bug, but we can, of course, we can never be sure that we discover that bug. But if it does report a counterexample, it should always be a valid counterexample. So I guess that's the notion of completeness in a way.
That sounds more like a soundness property, but yeah, okay.
All right, I think there's a question in the chat. I don't know if you have opened that one, maybe.
Shit. I guess maybe. I'm not sure how this works.
Otherwise, I can read it out loud.
Yeah, that would be better.
Yeah, so the question is, are equal inputs included in a set of preset things that we always test for, or does it have to randomly hit them both, right? So these, I mean.
I didn't hear the first part of the sentence. Sorry.
So the question is about how you actually generate these random test cases. So I mean, the probability of testing that both the to and the from accounts are equal, right? Is that included in some kind of preset configuration for your test, or is it just the probability that you somehow randomly hit two equal accounts as input?
Yeah. So this is actually one of the key issues that I had when I developed this testing framework, and it's a really good point. So it's, in general, it's more a problem of what do you do when you have a precondition that's very sparse. And well, there are two different ways of handling this. Either you can just still generate random input and then hope that you sometimes hit a satisfied precondition, and then just make sure that you run a lot of tests. So that's one way. The other way is making a specialized generator that, for example, in the example I gave where let's say precondition is that you have, the number must be a prime number. You could perhaps, well, prime numbers is maybe a bad example, but you could perhaps make a specialized generator which more often, or maybe always, only generates prime numbers, and then you would always hit your precondition. And all the property-based testing frameworks, at least the ones I've seen, and QuakeCheck in particular, have very good tooling for making specialized generators. So in this case, for example, with the transfer function, let's go back. Yeah, we require that from equals to in this case, and you could make a specialized generator which only generates transfers where the sender and the receiver is the same person. You could do that, but well, then now you're specializing your test with some specific knowledge about the attack. So it's kind of a mix between the two. What do you want, like a fully random generator of inputs, or do you want something that's specialized to whatever you're testing, but you don't want to use like too much knowledge about the attack that you're perhaps testing, or the bug that you're testing against. But yeah, it's a mix between the two. If you just generate completely random data, let's say completely random blockchain states and completely random states of this token contract, and completely random calls, for example, transfer calls, then you might not discover this bug. So you have to do something a little bit more smart than that. But I'm not sure I can explain how that works in a couple of minutes. But yeah, I hope that answers the question.
I think it does. Are there any more questions? All right, then I don't see anybody. So I guess thanks a lot, Mikkel. And we'll hopefully see you next Thursday.